All right, let's dive into a question that seems simple but is actually a massive puzzle for AI. How does a machine, which just sees a bunch of numbers, know that man bites dog and dog bites man mean two completely different things? Well, today we're going to crack the code on a really elegant solution to this problem.
I mean, think about it. This is a huge challenge, right? You've got the exact same words, but just by swapping them around, you totally flip the meaning. A language model has to be taught how to get that. It's not obvious to a machine.
For us, the difference is night and day. Man bites dog is a wild headline. Dog bites man, well, that's just a regular afternoon. But to a computer, these are just a pile of tokens. Without a sense of sequence, they're basically the same thing. The AI has to learn order from scratch. So how do they do it? Well, one of the most popular ways is this super clever mathematical trick called rotary position embedding. We're just going to call it RoPE. And the secret to how it works? It's all locked away inside a single equation, and we're going to crack it open together. And here it is. I know it looks a little intimidating, but I promise by the time we're done here, every single piece of this is going to make perfect sense. This formula is what tells an AI how much attention one word should pay to another, and it uses a really beautiful geometric trick to pull it off. Okay, so to understand the whole thing, we got to start with the absolute basics. Let's talk about its building blocks: queries, keys, and how they get paired up. First up, we've got the query vector. We'll just call it Q. You can think of this like a word sending out a search signal. It's asking a question, like, hey, who's doing the biting around here? Or what is getting bitten? It's basically looking for other words to figure out its context. And of course, if a query is asking a question, you need something that has the answer. That's the key vector, or K. The key is what each word uses to announce what it is. It's like a word holding up a sign that says, hey, I'm the one doing the action, or I'm a thing. It's just waiting for a query to come find it. So if we look back at our big equation, you can see them right there. We've got Q for our query word at some position M, and K for our keyword at position N. The whole point of this equation is to figure out how related these two words are, to measure how much they're aligned. Now, here's where it gets really clever, but it starts with a super simple idea. RoPE doesn't look at the whole long list of numbers that makes up a word's vector. Nope. Instead, it just groups them into tiny little pairs of two, and that simple step is what makes all the rotary magic possible. And you see this symbol here, this big E-looking thing? That's sigma, and all it means is add everything up. So we're going to do our little calculation on every single one of those pairs, and then we just sum up all those results to get our final score. Simple as that. So we've got our pairs of numbers. Now we get to the really fun part, the core mechanism. This is the rotary in RoPE. This is where the magic happens that gives the model a sense of order.
See, the really crucial insight here is that a word's absolute position, like if it's the 5th word or the 50th word, doesn't matter nearly as much as its position relative to other words. So the first thing we do is calculate m minus n, which is just the distance between our two words.
And this right here, this cosine part, this is the engine of RoPE. It takes that relative distance, m minus n, and it uses it to literally rotate our pair of numbers in a 2D space. So if words are really close, they get rotated just a tiny bit. If they're far apart, they get rotated a whole lot more. The rotation itself is how the distance gets encoded. Pretty cool, huh? But here's where it gets even more clever. It turns out not all of those pairs get rotated at the same speed. RoPE actually uses different frequencies, different speeds of rotation to capture all kinds of different relationships in the text. A really great way to picture this is to imagine each pair of numbers as a hand on a clock, or maybe a spinning dial. Some of these dials are spinning like crazy, completing a full circle for every single word that goes by. But others are spinning incredibly slowly, taking thousands of words just to make one full turn. And this table just shows you how wild that difference is. The pairs with a low index number, those are our fast spinners. They do a full 360-degree turn for every single token. That makes them perfect for figuring out the relationship between words that are right next to each other. But then you have the high index pairs, the slow spinners. Man, these things take over 6,000 tokens to make one full rotation. They're designed to capture those long-range connections, the ideas that link paragraphs or even whole pages together. So let's put it all together. What's the big idea with RoPE? Well, it teaches an AI about word order by focusing on the relative distance between words, not their absolute spot. It uses this beautiful, simple idea of rotation to encode that distance. And by combining fast and slow rotations, it can understand the grammar inside a single sentence and the big ideas across a whole document, all at the same time. It's just geometrically elegant. And that leaves us with a really fascinating thought. The solution to one of the hardest problems in language AI wasn't some ridiculously complex formula. It was just a simple rotation, a clean geometric idea. It really makes you wonder, right? If something this simple can teach a machine so much about language, what other fundamental geometric ideas are just sitting there, waiting for us to find them, ready to unlock the next big breakthrough in AI?